might have noticed in the previous video that my example experiment, does this medicine prevent colds? Well, expose everyone to virus, and then only give half of them the medicine. If the medicine group gets better quicker, and the no medicine group, they all die, then it looks like that medicine works. That's an experiment. Technically, it's a well-designed experiment, but there's some ethical problems with it. People sort of don't like being infected and then not given medicine. The study subjects might object. So there are some times where we have a question. We do know how we would do an experiment to answer that question, but for practicality or ethical reasons or a variety of other reasons, we can't actually run the experiment. What do we do then? Well, there's a couple things. There's a lot of things you can get away with doing to animals that you can't get away with doing to people. Like that, infect half of them, or infect all of them, give half of them medicine, give the other half nothing. People do that to animals all the time and don't go to jail. So, a lot of the times, if an experiment would be unethical to do to humans, you can get away with just doing it to animals. Aside from that possibly still being pretty unethical, you also get confounding variables. Just because something works in mice doesn't necessarily mean that that medicine is going to work in humans. There are some differences between humans and mice. You can't randomize and control for that. So, extrapolating from animal experiments to human conclusions is a little difficult. Sometimes it works, sometimes it's worthwhile, but it's definitely a complicating factor. And sometimes we don't like killing animals. So what else can we do? Preferably two people. Well, we can do anything we want, as long as we don't do anything to them. If they already did it to themselves, no problem. So, what if we could do like a history experiment? Okay, history experiment isn't the formal term. Observational study or correlational study are the technical terms. But they're basically history experiments where you just look at things that people do to themselves or already did to themselves. It's not the scientist's fault if they smoke and get cancer. He was already a smoker and he just got cancer on his own. I didn't do anything to him. I'm not a bad guy. I didn't do anything at all. He did it to himself. If people do the stuff to themselves, there's nothing wrong with collecting data on it. These kind of history experiments are weaker since you don't have randomization and you're not the one doing the thing. You're not introducing the difference. There's a lot of stuff that's not controlled for. So these correlational studies are a lot floppier and weaker. And they don't tell you which way the arrow of causality goes. Did A cause B? Did B cause A? Did C cause both A and B? But correlational studies do at least show where there is an association where, hey, we don't know which of those three things is happening, but we're pretty sure that one of those three is happening. We should research this more. Correlational studies help us decide where to focus our further research. and they're usually a lot easier to do than real experiments. Okay, so we like correlational studies, especially for us individuals who don't have a lab. We're just random critical thinkers. We're trying to get by in life. We can't really run too many of our own experiments, but we like to engage in experimental reasoning. So the cheaper and easier the experiment, the better, which is why we like correlational studies. They come in 3 varieties. One is a prospective cohort study. Let's say I had the hypothesis that smoking causes lung cancer. How would I test that? Well, in a prospective cohort study, I'd find a bunch of people who are smokers, find a bunch of people who are not smokers, and I'd just watch these people over years. Maybe I'd send them surveys once a year for the rest of their lives, and see how many people in their old age get lung cancer. Is it that they both get an equal amount of lung cancer? Or do the group who are smokers end up developing way more lung cancer than the group who are non-smokers do? I find 2 groups with different exposures, smoking versus no smoking, and then sit back and watch and see if a different rates of outcomes develop. And I just sort of guess that a difference in outcomes is due to the difference in their lifestyles, difference in smoking versus not smoking. That's a prospective cohort study. We could also do that backwards, called a retrospective case control study. Instead of looking at a bunch of normal people and waiting for something to develop, we go at the other end. We go to the hospital, find a bunch of people who are in the hospital with lung cancer, and then ask those people who have lung cancer, are you a smoker or not? And we compare the rate of smoking in lung cancer patients to the rate of smoking in the general population. Let's say maybe out of the general population, maybe 1% of people get lung cancer. But then when we go to the hospital and ask only people who actually have lung cancer, maybe 20% of them are smokers. 20% versus 1%. It looks like a lot more of the people who have lung cancer have a history of smoking. Maybe the smoking caused the lung cancer. That's a retrospective case control study. They're useful. Technically, though, these studies don't tell us which one caused which. Not very clearly. You can sort of get a feel for it and figure it out, but it's not perfectly clear. Let's say instead of smoking and lung cancer, we had sedentary lifestyle and heart disease. Does a sedentary lifestyle, not getting exercise, cause heart disease? Yeah, that sounds reasonable, probably. Or does heart disease cause a sedentary lifestyle? If your heart is bad, then you probably cannot exercise. And so you sit on the couch all day and have a sedentary lifestyle because of your heart disease. So maybe being lazy and not exercising causes heart problems. But then again, heart problems would definitely cause you to act lazy and not exercise. Which causes which? For all we know, maybe even a third thing like poor diet, eating a bunch of snacks and processed junk food causes both. Maybe it causes you to become too fat to be good at sports, and so you never exercise. And it independently, separately causes medical problems in your heart. Could be that too. An underlying factor causing both. And a correlational study like the case control and cohort, they don't do as good a job of telling us which one is which. Like in a real experiment, you can introduce the thing you're trying to study and take it away and put it back. Take it away. Give it to some other people. Take it away, put it back. And you can turn it on and off like a light switch. You're actively introducing the independent variable. So you can see if the outcome, the dependent variable, lags behind the introduction of the thing in time. You can see how consistent the correlation is. With a true experiment, since you're doing the thing and you can stop, you can start again, you have a lot better control about the first thing you're studying, which makes it easier to interpret where the effect came from. It's a lot easier to reliably tell whether A caused B, or B caused A, or C caused A and B in a true experiment. If you're just doing correlational studies, you might need quite a few of them to really figure it out. So correlational studies suck. They're lower powered, but the good thing about correlational studies is a lot of times they're easy to do. So they're for lazy people? Yeah, lazy people or people who are in a hurry. There's say there's a epidemic going on and you'd like to make a decision about public health very quickly because people are dying every day. You could wait for a real experiment, but if that takes a month, that's a lot of dead people, and we don't like unnecessary deaths. Sometimes a correlational study will give you enough information to make an informed decision, and gets you enough information way quicker than an experiment would get you results. Even though the results of the experiment would be higher quality information. The third and weakest kind of correlational study gives us the best example of one instance where a correlational study gave vague, imperfect information, but that was still good enough for saving lives. So in an ecological study, you're just comparing two things and seeing if they sort of match up. Do you see a correlation? No correlation at all? Negative correlation? They stay away from each other? A famous early correlational study was from London in the 1850s. It sort of was a crappy place back then. Sometimes literally crappy. And you got diseases spread by feces, such as cholera. So it's London in the 1850s. There's a cholera epidemic. And back then, Western medicine was pretty bad. So doctors are seeing cholera patients. They can't really do anything. A lot of their patients are dying. The doctors feel bad and incompetent when their patients die. So there's this one doctor, John Snow, who's feeling bad about a lot of patients dying from cholera. It's making him look incompetent. So, at some point, he makes a map. He makes a map of where the cholera patients live. Like, he's got maps of London around and just starts putting pins in it for the locations of the houses of the cholera patients. And he notices something. The location of the cholera patients isn't completely random all over London. It correlates with a certain feature. That feature was distance from one specific water pump. So he guesses that something in that water pump was causing the cholera disease. He did it in formal vocabulary. He conducted an ecological study correlating cholera condition, have it or don't have it, with distance from the Broad Street water pump. And he found a big negative correlation between likelihood of having cholera and distance from that pump. He sort of had his map. Most of this was just in his head. And so one night he went out and took a wrench and took the handle off that water pump. And magically the cholera epidemic started going away. Obviously, since the pump didn't have a handle, people stopped using that water pump and would go somewhere else for their water. When they stopped using the poison water pump, the disease started going away. So his guess, based on a very informal ecological study, turned out to be right, and probably saved quite a few lives in London in 1854. And the interesting thing is that back in these days, they didn't know, they didn't take water from the well, culture bacteria, see, yep, cholera bacteria in that water. Stop taking water from this pump. They didn't culture bacteria from that water. They didn't know which bacterium caused cholera. They didn't even know that bacteria caused disease at all. At this point, 1854, the germ theory of disease wasn't well known. I'm not sure that this guy knew about it at all. But he didn't need to know those technical details to take action, even correct action, that saved quite a few lives. By operating just on his correlational study, or ecological study, looking at the map of where the patients are, they're next to this thing. Well, get rid of that thing. And maybe the patients will get better. With that very informal correlational study, he was able to make the right decision. Even though he lacked a lot of scientific technical knowledge. By having good episteme, being able to do this correlational study, mostly in his head, and uses a logical imagination, he was able to get the right answer and save a lot of lives, even though he didn't even know that bacteria cause disease. The state of science just wasn't there yet. By having a good analytical imagination, he was able to make the same decisions that we would far later when armed with much better technology and a more advanced state of science. Having good logical imagination to do these almost thought experiments and correlational studies in his head allowed him to behave like a far more modern person and save quite a few lives. So correlational studies definitely have a place, and it's really useful to remember that, because as technology progresses, it gets easier to do some experiments, and experiments give us cleaner data and stronger conclusions, so we like real RCT, randomized controlled trial experiments better. And some people over-extrapolate that to saying RCT is a real science, but correlational studies suck, don't do those. Yeah, there's some truth to that. But if you only stick to perfectly kosher, true experiments, your rate of discovery is going... You'll be sure your discoveries, but you'll be slow in making them. And sometimes, if it's just me, I don't have a lab, I can't do much real science. Or if you need to act quickly, like people are dying today, we need to make a decision now, not a month from now. Correlational studies help us make better, help us make quick guesses that are better guesses. You could say that epidemiology, the branch of science that these correlational studies generally come from, is one of the major areas where critical thinking gets applied today. Like, a lot of what I learned about critical thinking actually came from a course on epidemiology. And hopefully it'll help you too.